Hey everyone, it's Justin again. You've learned a lot about the reciprocal function 1 over x. Now we're going to start exploring a more general type of function, the rational function. We'll start with how to identify discontinuities. By the end of this lesson, you should be able to identify the types and locations of discontinuities in a given rational function. First, we'll define what a rational function is, and then we'll define discontinuities. We'll learn about the two types of discontinuities found in rational functions, and then we'll practice a couple of examples. In the last few lessons, we've been focusing mainly on the reciprocal function 1 over x. Let's define a more general term, rational functions. A rational function is a function that is the ratio of two polynomials. This is one example of a rational function. But these polynomials don't have to be big and complicated. Technically, 1 and x are monomials, which are a type of polynomial. So 1 over x, the reciprocal function, is also a rational function. All of these are examples of rational functions. We'll be exploring the properties of these kinds of functions in the next few lessons. Today, though, we'll be focusing on their discontinuities. So let's define the term discontinuity. A discontinuity is an x value on the graph of a function at which the function is discontinuous or does not exist. For example, this line is continuous. It's all in one piece and it exists at all values of x, so there is no discontinuity. But take a look at this graph. This line is broken up into two pieces. It's no longer one continuous piece. Therefore, this graph has a discontinuity. We use the x value to describe this discontinuity. Here, the x value where this happens is at x equals 1. So we say the function has a discontinuity at x equals 1. For practical purposes, you can think about this as whether or not someone could trace the whole graph in one continuous motion, or if the tracing gets interrupted somewhere. For example, on the first graph, we can start on the left and go all the way to the right with one continuous movement of our pencil. On the second graph, though, we would have to stop tracing when we reach the end of the first piece, and then pick up the pencil and restart on the second piece. If we're looking at our movement from left to right, this happens when we reach the value of 1 along the x-axis. That's why the function has a discontinuity at x equals 1. The graphs with which we have been working for the past few lessons, various transformations of the function 1 over x, all have discontinuities in the form of vertical asymptotes. Notice that only the vertical asymptote causes a discontinuity. As we trace these graphs from left to right, the horizontal asymptotes won't cause us any problems. The part that can't be traced is having to cross the vertical asymptote to draw the other side of the graph. So the vertical asymptote in this middle graph gives us a discontinuity at x equals 0. And note that x equals 0 is also the equation of the vertical asymptote. On the graph of 1 over the quantity x plus 2, remember that a horizontal shift moves the vertical asymptote. So this function has a vertical asymptote at x equals negative 2. That means the discontinuity has also been shifted to negative 2. That makes sense with the function 1 over the quantity x plus 2, because negative 2 is now the number that would make the denominator 0. In fact, the discontinuities in all of these examples are at the x values that make the denominator 0. This brings us to the main point of this lesson. In a rational function, the list of values that make the denominator equal to 0 is also the complete list of the function's discontinuities. So, if we're looking for discontinuities in this function, we can set the denominator equal to 0 and just solve. The numbers we get from that will be the discontinuities of the graph. Even without actually drawing the graph, we know that if we plug in a 2 or a 7, we would get 0 in the denominator. So when drawing this graph, the tracing would get interrupted for a moment at 2 and at 7. since the function doesn't exist at those x values. That means there will be discontinuities there. Now that we know how to find the discontinuities of rational functions, we need to learn the two types of discontinuities that can be found in these functions. The first type is a vertical asymptote, as we've seen many times before. These happen at any x values that make the denominator 0, but not the numerator. So what happens when an x value makes the numerator and denominator 0 at the same time? Take a look at this function. To find the discontinuities, we would solve for all values that make the denominator 0. Those values are -1 and -2. So those are our discontinuities. Now, look back at the original function. We could cancel a factor of x plus 1 in the numerator and the denominator, and that would leave us with just 1 over x plus 2. That's actually exactly the same graph that we used in the last example. But there's an important piece of information from the first version of the function that we shouldn't forget about. Take a look at both versions of the function, the original and the simplified version. Can you see what information the simplified version is missing? The new version looks like it only has a discontinuity at x equals -2. But the original version also had a discontinuity at x equals -1. So what happened? In this step, we canceled the factor of x plus 1 in the numerator and denominator. What would happen if x were equal to -1? Those factors would each be 0, and we can't cancel out 0 over 0. When we cancel a factor with a variable, we need to account for the discontinuity that was created by this factor. The method we'll use here is to write for x not equaling this specific value. The number we put is whatever value of x would have made the canceled factor 0. So in this example, since we canceled x plus 1, we write for x not equal to -1. How do you think this will affect the graph if this function is the same as 1 over x plus 2, except that it has an extra discontinuity at -1? The factors that end up canceling don't affect the graph at all, except for causing it to not exist at -1. We can graph the simpler version of the function, 1 over x plus 2, but we put a hole at the x value of -1. The hole shows us that at this particular point only, the graph does not exist. This also means the hole is a discontinuity. If we were tracing this graph, we would have to pick up our pencil to cross over that hole. In general, a hole occurs at any x values that make the numerator and the denominator 0. To find holes, find any shared factors between the numerator and denominator, and solve for when those factors are equal to 0. Before we get ready for some examples, let's take a look at a rational function where the polynomials are in an unfactored form. In this case, factoring may be super helpful to find the discontinuities. For example, try factoring the numerator and denominator of this function and see if you could find the x values of the discontinuities. Do you have an answer? If we factor an x out of the numerator, we get x times x squared minus 9. In the parentheses, we have a difference of squares. So the numerator can be factored as x times x plus 3 times x minus 3. In the denominator, what two numbers would multiply to make -18 and add to make +3? Those numbers are +6 and -3. So the denominator can be factored as x plus 6 times x minus 3. The discontinuities would be at the values that make the denominator 0. So -6 and +3. X equals -6 would be a vertical asymptote because it only makes the denominator 0. X equals 3 would be a hole because the factor of x minus 3 appears in both the numerator and the denominator, resulting in 0 over 0. As we move on to examples, keep that important distinction in mind. If a value of x would make the denominator 0, it's a discontinuity. If only the denominator is 0, it's a vertical asymptote. And if it makes both the numerator and denominator 0, it's a whole. This corresponds to whether the factor that gave us that x value is only in the denominator, or if the factor is in both the numerator and the denominator. All right, let's try out some examples. List all the discontinuities of the following function. Do you remember that first step that might help? Factoring is a really good place to start. So try factoring the numerator and denominator now. Did you start by factoring an x out of both the numerator and denominator? After that, we can factor inside the parentheses in the denominator, since that's a difference of squares. At this step, you might notice that we could cancel some factors, but this actually won't help in finding the answer to our question. In fact, it may actually distract us. We're trying to list all discontinuities, and the discontinuities are what makes each factor in the denominator equal to 0. We don't want to cancel factors and ignore the discontinuities that those factors cause. Instead, let's just go ahead and solve for each factor equaling 0. We get x equals 0, -1, and 1. The list of x values that make the denominator 0 is also the list of discontinuities, so that's our answer. We'll do one more example. Which type of discontinuity, if any, is found at the x value of -2 in the following function? As before, it's a good idea to start this by factoring. What's the factored form of this rational function? Do you have your answer ready? In the numerator, the numbers that multiply to -6 and add to -1 are 2 and -3. And the denominator is yet another difference of squares. The first question we should ask ourselves now is -2 a discontinuity? Since x plus 2 is a factor in the denominator, -2 will indeed make the denominator 0. That means it is a discontinuity. To see which type of discontinuity it is, we need to check and see if x plus 2 is also in the numerator. Well, looky there. This factor is indeed in the numerator as well as the denominator, which means that this discontinuity is a whole. In this video, we learned about two types of discontinuities in rational functions: vertical asymptotes and wholes. This will be super important to remember as we learn more about these functions and their graphs in the next few lessons. See you then. Hey.